If you are trying to push true 8K video, so we are talking a massive 7680 by 4320 resolution running at 60 hertz across a stadium or a large commercial space, a standard copper cable will simply, well, it'll just choke on the data. Okay, let's unpack this. Welcome to today's deep dive, where we are looking at a highly technical spec sheet from HDTV Supply for the Avenview FO8K-DP-10-MM DisplayPort cable. Our mission today is to decode exactly how engineers are solving this physics problem of transmitting staggering amounts of data over incredible distances, without losing a single pixel.
Right, because copper has a very strict physical limit. Pushing 8.1 gigabits per second per lane over 30 or, say, 100 feet of copper, it degrades the electrical signal so much that the screen basically just goes completely blank.
It's like trying to force a roaring waterfall through a standard garden hose, and it just backs up.
Exactly. It just can't handle the volume. So the Avenview cable circumvents this using an active optical cable or an AOC structure. And what's fascinating here is not just the use of fiber optics to bypass copper's limits, but it's the extreme miniaturization involved.
Yeah, because we aren't talking about those massive server room fiber transceivers here. I mean, the translation from electricity to light happens right inside the standard DisplayPort connector that you just plug into your computer.
Right, exactly. The transmitter plug itself houses a microscopic 850 nanometer optical source.
Oh, wow. And it's using multimode glass fiber, right? Meaning the glass core is wide enough to bounce multiple light rays or modes down the line simultaneously to, handle that massive 8K bandwidth.
Right. Multimode is key there. It allows for a massive amount of throughput.
It's kind of like having a microscopic Morse code operator firing lasers billions of times a second to perfectly recreate the digital signal.
And doing it flawlessly over hundreds of feet. But that introduces a pretty massive engineering hurdle.
Wait, if we are firing lasers down a glass tube, I mean, light is strictly a one-way street here. A monitor and a computer don't just blindly dump data. They constantly have to handshake over resolution and copy protection.
Yeah, that is the inherent challenge of optical transmission.
Right, so how is this cable actually handling that required two-way traffic without relying on a parallel copper wire?
Well, to solve it, the cable doesn't just have fibers for the video feed. It actually includes a dedicated single-channel multimode fiber specifically for two-way communication.
Oh, I see. So it has its own dedicated lane for talking back.
Exactly. It manages hot plug detection, meaning it instantly recognizes if you plugged into an 8K display or an older 4K monitor, and then it adjusts the output accordingly.
So it's actively negotiating the connection the whole time.
Yeah, and it's managing the DPCP and HDCP protocols in real time as well.
Those are the strict security handshakes, right?
Yeah.
Proving to the source device that your monitor is legally authorized to display the copyrighted content.
Right, exactly. Without that two-way optical channel instantly validating the connection, your screen stays dark, regardless of how much video data you pump down the main fibers.
That's wild. But packing an entire active negotiation system and microscopic optical transceivers into a standard plug, I mean, that can't come cheap.
No, it definitely doesn't.
You are looking at, what, $480 for a 10-meter version, which is about 33 feet. And if you need to run it 328 feet through a stadium, that 100-meter version costs $3,320.
It is a serious investment for a serious bottleneck. But I think the most impressive engineering feat here might actually be the power efficiency.
Really? With all those lasers firing?
Yeah, converting electricity to light, pushing 8.1 gigabits per lane over hundreds of feet, and translating it back, it requires a mere 0.3 watts of power.
Wow, just 0.3 watts? How is that even possible?
Well, it achieves this because those 850 nanometer micro lasers, they're known as VCSELs, they require almost zero startup current. So they generate massive bandwidth without generating excessive heat or, draining power from the source device.
Yeah. Getting all that distance and bandwidth for a fraction of a watt is just incredible. I mean, we've moved from passive copper wires to smart cables that actively translate our heaviest digital payloads into light, just to conquer physical distance.
Which raises an important question for you to consider. As our personal data consumption multiplies every single year, how long will it be until every ordinary household charging cord or display cable requires these microscopic light translators built right into the plugs just to keep up with our devices?
That is definitely something to mull over the next time you plug in your phone or laptop, because as the data gets heavier, those old copper wires are, well, they're just running out of runway.